Hello and welcome to the second half of the semester. So our next lab, we're going to do a mechanics lab with materials testing to see stress strain diagram for rubber. And I'll show you some applications of why that would be important. But to get started on that, we're going to actually design an experiment. And this will be twofold. One for the lab for class that we're going to do with stress strain diagrams, and the second objective is for you to design an experiment for your project. So decide on what kind of inputs you're using, what kind of outputs, so goals, and how you want your project to function. To get started, let me just show you a couple of textbooks. So here is Principles of Instrumental Analysis. This is actually from a chemical engineering curriculum. And it goes through all of the instruments used to kind of measure chemical properties. So everything from here's properties of electromagnetic radiation, optical spectroscopy, looking at HPLC, high performance liquid chromatography, gas chromatography. So a bunch of all the different equipment that you have to measure things in an experiment. And then once you have that data, of course, you have to analyze it. So there's a lot of classes that you might take with statistical methods so here's Introduction to Statistical Quality Control. If you're going into mechanical engineering, you might look at getting certified with Six Sigma, which is a quality control kind of a thing. Here's basic data collection and analysis. So each of these books I'm showing you, this goes along with an entire semester-long course. It's looking at how to collect data and analyze data, apply the correct trend lines, and understand what you're looking at, signal-to-noise ratio. Here's Applied Multivariate Statistical Analysis. I think this might be a grad level book, but it just goes on and on and on for designing experiments and looking at data and really understanding all of the components that go into that data, correlation versus causation. So this stuff can actually get really complex, and we're just going to look at the very tip of the iceberg here for what you'll start getting into. Okay, purpose of experimentation. So of course you want high quality for low cost, easily assembled, easily produced, that's safe, environmentally friendly. So all of the goals for functionality and everything that's going into your project. So the purpose is just to create the most optimal results for your product. Okay, the experiment is changing your input to get your desired output. And some examples of this, let me just scroll down here to some of these flow charts. So inputs can include things like the personnel, materials. Are you making this out of wood or metal, plastic, cardboard? What kind of equipment are you using, and what maintenance and cost goes along with the equipment? Policies, rules, regulations for what country you're making this in, procedures, methods, environment. Are you doing this, outside in the hot sun? Is there temperature, pressure, corrosion considerations? So you have all of these inputs that can change how everything is produced. Okay, so you look at the outputs, how strong your product is, how safe, how easily usable it is, and there's quite a few examples in here of various different scenarios. So here's developing an environmental stress screen test. So you have temperatures that this is being loaded under, thermal cycles, humidity levels, vibration for fatigue failure, the time that it's exposed to this. And after all of these inputs, they will measure the number of defects in the material after it's subjected to these different inputs. Okay, or here's computer network performance analysis. So you're looking at maybe voice calls that are blocked and delay times and utilization times. Here's a mold injection. So for molded parts with plastic, you're looking at holding pressure and temperature, holding time, gate size, how fast you're pressing the material into the mold, how much regrind. So if you're having to do a lot of cutting and polishing after the fact, what kind of moisture content is getting in there, and the outputs will be the thickness, and when it cools down, how much is the size going to change, how many defective parts are going to come out of this. If you're making 100 or 1,000, how long is that mold going to last? So you can kind of scroll through a few of these examples and get an idea for some of the inputs and outputs that are present in some common projects. Okay, so thinking about data and data collection, the first thing you're going to do is go to the literature and see what's already out there. So you don't want to, start completely from scratch. There's a lot of data and analysis out there already. So you look at what people in the past have done. Sometimes you won't be able to get this information because it will be proprietary from various different companies. So, do what you can to network. And a lot of times the data, you won't have all of the information for, exactly what pressure was going on that day or humidity. Maybe they didn't record that information that was really important. But it's at least a ballpark, you have to start somewhere so that if you start measuring something, you know what you should be aiming for and if you're completely off or not. Okay, then you start designing an experiment for taking your own data. And you have these input factors and you want to know, how should I change the inputs and measure the output? So let's say you have, I don't know, mold injection, and you want to look at pressure and temperature dependence on what's happening to that part. And so you decide to test this at some high pressure and a low pressure, and then maybe a high temperature and a low temperature. So just a high and a low for each of these inputs. And coming out of this, you will look at how many of those molds were successful, right, that met some kind of criteria. If you change one factor at a time, so this is one experimental method where maybe I will hold the pressure constant and then just change the temperature. Or I will hold my temperature constant and just change my pressure. Well, if I look at this one at a time methodology, what you'll notice is that I'm actually missing a combination. So look at this and see if you can see what combination is missing. So I have pressure 2 and temperature 2, but I don't have any data for pressure 2 and temperature 1 combination. So I'm actually missing some of the combinations that are present for this one factor at a time. So this is a commonly used practice, but actually not very good, because sometimes you can miss some combination that might be the really important scenario that would be the best result or maybe a really horrible result. But the better thing to do is to use what's called a robust design, where you're actually looking at all of the different combinations of inputs. Okay, so you're looking at all the interactions between factors, and you want to get each data point on here. So you want to get pressure 2, a T1 and T2. Okay, so if you're going to look at every single combination permutation, that is called a full factorial design. And it works if you only have a few inputs. So like if you only have temperature and pressure, say. But if there's more than just a couple of inputs, and most systems have actually quite a few inputs. So you could think of something like the gas mileage on your car. What goes into the gas mileage of your car? Well, your tire pressure, and is this city or country miles, and who's driving the car and how are they driving it, right? When was the last time you got an oil change? What kind of gas are you using? Are you going up a hill? Are you in Kansas? So you can start seeing all of the different factors that would go into something as simple as what's the gas mileage in your car, right? And most systems are like that, where there's quite a few different input factors. So let's say there's 12 different input factors, and you're going to test each of those input factors at 2 different values. So maybe your tire pressure is good and you have flat tires or something. So you have 2 different scenarios. You're using this kind of oil or that kind of oil, regular or premium gas or something. So you have 2 different scenarios for each of those inputs. And there's 12 different input factors. What that translates to, if you're going to do a full factorial design, is 4,096 experiments that you would have to run, which is huge. You know, that's not going to be something that you're going to be able to do. So the next step down is what's called a robust design, where you say, well, there's no way, I don't have enough time to test every single combination of all the different inputs going into this, and it feels overwhelming. And this is where you get into kind of your statistical classes to trying to decide what combinations are the most important to test. So, you know, maybe there's a few things that you can't change and you can't control, so might as well, you know, give up on trying to change it anyways. You're not going to experiment with that. And there's quite a lot of math involved to really wire out. But good experimental design, this is going to determine the quality of your product. So if you're in competition with other people around the world and trying to produce the most energy efficient and stable and best widget, then you're going to want really good experimental procedures. Okay, so figuring out your experiment. State your goals. When you were making your decision table for your project, you had goals in mind for that. So safety, cost, functionality. So go back to those goals, and that's kind of the point of your experiment, is to achieve those goals that you've already stated. Background research, again, hopefully you're already to this part of your project as well. And so you're gathering information about what other people are doing and analysis, operations. And this will then get you into your list of inputs. So do you have a materials list put together for all of the different things you're going to build your project out of? And for this semester, this is just an introductory class, and you might just be making a prototype, a model, rather than the real thing. But it would be good for you to research that if you did have more time and more resources, what material would actually be best for you to make this out of, or what battery is best to use, what power source is best. So put in a list of all of your inputs and then all of your outputs. So this is more of your goals again. Okay, so your objectives, how are you going to measure your input? And this is where we want a quantitative analysis. So where you're actually writing down numbers, repeatability. So you're going to test the same thing a few times to see if you get repeatable results. And think about high levels, low levels, different scenarios for how you can change those around. And we'll do that for the stress strain for the rubber band again. And I also want you to put something together for your project. So let me just pull over this example Excel sheet. So you can put class, your names in here, experimental design, and here are some example inputs. So what material are you using? Wood, metal, plastic, cardboard. Equipment. So when you are carving up the wood or using a machine shop for your metal, or a mold or a 3D printer for your plastic, or a laser cutter, or X-Acto knife for your cardboard. Okay, so think about how you're going to take your raw materials and turn it into, and there's a wide variety of equipment that could be used. And again, you might not have that equipment on hand right now, but if you're planning for the future, for expansion, what equipment would you use if you had access to it? So go above and beyond what you're actually doing this semester to kind of what you could be doing, and in the best scenario, what would be best for equipment. Procedures, so what kind of heat treatments for metals? What kind of surface finishes are you using for the wood? extrusion temperatures. Are you using some kind of a special folding procedure for sheet metal or cardboard? And while you're doing this, what environment are you working in? So temperatures, pressures, humidity. Are you at the coast? Are you working in a corrosive, salty environment? Okay, so those are some of the inputs that go into here, and then here's some outputs. So maybe you're going to measure corrosion resistance. If you're going to put it in acid or salt water or just regular water, humidity, put it out in the sun and see if it's going to fade in the sun. How is this going to age? And some of these tests might take a while, so you might get creative. If I put it in the oven for 3 hours, is that going to be similar to what it's going to be, over the summer or something? Fatigue failure. How could you measure fatigue? Hardness, strength. So the stress strain diagram we're going to do next week and set up just the tables for it this week. That is a very common test that's used for materials testing. And for the strength, so we're going to do just test a rubber band because it's simple. You have it at home, and it's an easy curve to make. In the real world, like if you're testing cement and you put it under hydraulic machine and look at compression testing, or for metals, and it's a huge, again, hydraulic machine that does tension testing. But you can get the same kind of a curve with a very small sample for rubber, and it has a very unique stress strain diagram actually, so it's kind of interesting. So you can look at different loading conditions. Are you loading it fast or slow? Sometimes you have creep if you're loading it very slowly. And then also treatment. I will give you extra credit if you find a treatment that you can do to a regular old rubber band to strengthen it. And I'll give you a hint. Why are car tires black? That has to do with the treatment that will strengthen rubber a little bit. Okay, and that's again something that you can maybe do with some common household chemicals. So play around with soaking that rubber band, cooking it, freezing it, doing a few things to it to see how those different treatments would change the properties. Okay, how about thermal and electrical conductivity? So if you have any kind of electrical components to your project, make sure that all of your wiring is not going to get shorted out. It's not going to shock anybody. If this is a civil engineering project, maybe you want to make sure your air conditioning bills are low or something. Safety. So is this something that's going to light on fire? Is it carcinogenic, hypoallergenic? Like what kind of population is going to be coming into contact with it? So you want something toxic to people. How reactive is it to everything from salt water, to think through what kind of environments it could find itself into. Stability, if you drop it, will it explode? That's some more chemical engineering, I guess. Environmental impact. So when you're choosing what type of plastic to use, does it really need to last 1,000 years, right? Or is it okay if it starts degrading after a year? So those kinds of things can make a big difference when you're deciding how your project should be built. Just the density of the material. How expensive is it going to be to transport it? You want something maybe lightweight that's easy to lug around and is going to be more energy efficient, usually, if it's lightweight. Look at the melting point. So like the PLA for 3D printing, that stuff will melt on the dashboard of your car. So, that's not too great. Volatility, if you're dealing with liquids. And you can go through kind of all of your senses. So what does it taste like or smell like, feel like? What's the surface finish? Optical properties. Is it reflective, transparent? What's the color of it? This is, civil engineering. If you want windows in your building, acoustic properties. So if you have a motor, do you want that motor to sound big and mean and tough, or do you want it to be quiet and not wake up the neighbors? So insulating or reflective materials with acoustic properties in mind. And of course, economic. So you're looking at the cost of materials, the regulations of where you're building this, scarcity, how to transport it, ease of manufacturability. So there's a lot of different outputs and inputs. And for your project, of course, you're not going to test all of this, but I want you to think about what would be the most important thing, and given your time constraints, what could you effectively experimentally gather data for and test by the end of the semester. So define a couple of inputs that are super important to you, and then define the outputs, something that you can quantitatively measure. So take data for how strong it is, or how easy it is to bend, or how much it costs. And then set up some kind of experiment to get that information. Okay, so hopefully that is a good start. Read through the notes over here for some example experimental design. You can get through, I'm sure all of you have had classes, whether it's physics or chemistry, that you've gone through labs before. So get those lab notebooks open again and think about how you took data, what kind of equipment you used. And sometimes it involves actually making the equipment to perform the experiment. So a lot of grad students do that. They have to make their own experimental testing equipment. One more thing we need to talk about is uncertainty analysis when taking data, and I will save that for the next video.